Oh, yeah. I prefer the dark, to be honest. I swear. But we'll have this on too. Oh, yeah. Oh, yeah. All right. If you are zooming, if you get a chance, go to Blackboard and grab there's in the module 2A, there's a document in that supplementary readings folder that says bond strength chart. Go ahead and download that. You don't have to have it right now, but it's going to help you. So eventually you need to have it in your toolbox. Go ahead and share. Yeah, I prefer it like this. All right, so we're going to start here and we're going to start walking these reactions down. So we're going to use, the last thing we talked about on Wednesday was delta H. We started talking about some thermodynamic stuff, right? Like the energy and we did, one thing I missed, but I sent it when I sent the video was delta G, which is the Gibbs free energy. We'll talk about that. It's the difference between the products and the reactants, but it mirrors delta H. And so we're going to start out with this first reaction. Let's do that. We're going to walk it down. And then let's take this. We'll take this and cut it. Put it. All right. So with that reaction, we'll zoom in some. All right. We're going to walk this down in this way. We're going to identify the nucleophile, identify the electrophile, put in the arrows, and then we're going to talk about whether the reaction is endo or exothermic. And we're going to prove it. All right. We're going to prove whether it's endo or exothermic. All right. So in this particular case, you have the product. What happened? What happened in going from star materials to product? What changed?
You broke the pi bond.
Broke the pi bond.
From your oxygen.
Yep.
Made a sigma bond with it.
Made a sigma bond to nitrogen. Is that right?
Yes.
Okay, good. So that's what happened. What type of reaction is that?
Is that it's not a
Right.
I think, what is that? Or addition.
Addition. When I start with a double bond and I end up breaking it, by adding some nucleophile to it, it's addition.
So with elimination, you would be ending in a double bond?
Yeah, exactly. Elimination always gives you a double bond in the product. Oh, that's good. All right, so we know it's an addition. Let's put the arrows in. Where's my nucleophile? Yep, so this is nucleophile right here. By default, this is the electrophile. Excuse me. And then where is the nucleophilic site? I mean the electrophilic site in the electrophile. Oxygen has 2 lone pairs already, very electron rich. There's got to be something that's electron poor. So it would be the carbon, right? But the dipole is, this is partially positive, that's partially negative. I'm sorry, wrong backwards. It's positive, and this is partially negative. So it's the carbon. So when we draw arrows here, we're going to draw them here, here. And what else? What else do I need to do? Okay. Anybody not following that part? All right, so that's how we got to our product, which is over here. Now, in order to tell whether it's endo or exothermic, we need to know some more information. We need to be able to, first we have to calculate delta H. How do we do that? Anybody?
You take the sum of your broken bonds.
Bonds broken minus what?
Bonds formed.
Bonds formed, right? So it's going to be bonds broken minus bonds formed. And if you break multiple bonds, then you just sum them up. All right? What bond did I break? CO bond. And then I made what?
Sigma bond.
So I made a CN sigma bond. Good, excellent. Everybody following that on Zoom? So I broke a CO pi bond and I made a CN sigma bond. In general, for any given reaction, the idea is to go from weaker bonds to stronger bonds. If you do that, the reaction is going to be exothermic. If you go from strong bonds to weak bonds, it's going to be endothermic. Not favorable. All right, so let's look at the chart. And let me spend some time explaining that. So here, I have my multiple bonds down here. So the energy to break a CO pi bond is either 177 kilocalories or 741 kilojoules per mole. Because 1 kilojoule is 1 kilocalorie is 4.81 kilojoules. So that's why the numbers are different. All right. So this is kilocalories or kilojoules. You can use either one, but you can't use both. You follow? Because you can't subtract kilojoules from kilocalories. You got to convert one to the other. So for CO pi, I like to use kilojoules. But the numbers are bigger and the differences look more dramatic. Kilojoules per. All right, and you'll have this chart on the exam when you take an exam. So now I'm looking for a CN sigma. So here's carbon. Here's nitrogen. And then on the carbon line, what is that? That's 305. Follow? Y'all follow that? So 305. Kilojoules per mole. You good so far? If we just subtract those two, what is that? 436? All right. I'll do some common core up there.
400.
I'll just joke. How much? 436?
That's what it is.
Positive or negative? That matters, right? We got to keep the sign. The sign of the number is going to tell us if it's endo-exothermic. So delta H for this reaction is positive 436 kilojoules per mole. I went from a strong CO pi bond to a weak CN sigma bond. Got a question? Anybody? No? Sure. Positive. Anybody online with a question? So plus 436 is the delta H.
I have a question.
Go right ahead.
When it's on the test. When it's on the test, will you ask us if it's addition or elimination? We access to state that
Oh,
also, okay.
everything is fair game. Oh, I mean, it's fair game. It's like a buffet. You might pick chicken, you might pick steak, you might pick, collard greens, whatever. But it's all available, right? You got it. You understand. All right. So the fact that delta H is positive tells us everything. We can extrapolate all this other information that the question asks. Let me go back to the question because it asks a lot, right? It says identify the nucleophile electrophile. We did that. Is it a substitution, elimination, rearrangement, or addition? We did that. Calculate delta H. Is it exothermic or is it endothermic? Now that's what we're doing. And we're going to draw an energy diagram for it as well. All right. So right here, the fact that delta H is positive, this is and such a big number, right? This is highly endothermic. Highly endothermic. That means it takes a lot of energy to get this reaction to go, right? And it may be lost on you because kilojoules seems so esoteric. That's a lot of energy. I mean, a lot, right? If you think about it in kilocalories, 177 kilocalories, that's 177,000 because a kilo is 1,000, right? That's a lot. Yeah, that's a lot. So it's endothermic, we know that. And then all the other stuff we can infer from delta H being positive, we're going to do. So if delta H is positive, then delta G double dagger, which I think we talked about the other day, did we not? Activation energy. That's going to be high. Activation energy. We don't know the number, but it's going to be high, right? High activation energy. So endothermic reactions have a high activation energy. And if you calculate delta H, you can infer from that all this other information. So delta G double dagger, which is activation energy, is going to be high. Delta G, which is the Gibbs free energy, right? It's also going to be positive because delta G and delta H are related, right? Because remember this from CHEM, delta G equals delta H minus T delta S. Is that right? So we negate the entropic factor. Delta H and delta G are roughly equivalent. So if delta G is positive, or delta H is positive, then delta G is going to be positive. And then the other part that we can infer is the equilibrium constant, K and Q. It's going to be less than 1. Good question. Remember the equilibrium is the products over the reactants? Is that right? Y'all remember that from GChem part 2?
Yeah.
All right, so if, let me explain this in terms of the energy diagram. So this is the energy diagram for just a basic endothermic reaction. Right, well, this is time. This is energy. On the bottom. Increase in energy. So as you go up towards the ceiling, energy goes up. All right. So for an endothermic reaction, there's not a lot of product made. But there's a whole bunch of reactants left over. All right, so if this is a quotient, not much product made for endothermic reaction. So this number right here is going to be small. There's a whole lot of reactants left over. So that number is going to be big. Small number. Large number. So when you divide it, right, the quotient is going to be less than 1. If the denominator is larger than the numerator, it's going to give you a fraction. Is that right? Or a decimal. So that's why KEQ is less than 1. We don't know any of these numbers specifically because those are all experimentally calculated. But we can infer from the delta H and the fact that the reaction is endothermic, we can make an inference to all these other numbers. What is delta G double dagger? What is delta G? What is delta H? And what is the equilibrium constant? And just for the sake of having the information, this right here, this gap between reactants and products, that is the DX energy. That's delta G. And it is products minus reactants. Right? The energy. Right? So the product minus the reactant. And if the product energy is higher than the reactant energy, and you subtract them, you're gonna get a positive number. If it's the other way around, you'll get a negative number. Is that right? If this number is bigger, so P is bigger than R. If P is a bigger number, then you're gonna get a positive number. If R is a bigger number, you'll get a negative number. Are we okay with that? Any questions about anything? So we know everything, we know a lot about this reaction now. We know it's endothermic. We know it has a high activation energy. We know that the KEQ for it is less than 1. And we know the actual delta H, we calculated. Bonds broken minus bonds formed. All right, questions? Any questions? Any questions from anybody online?
I have a question. Can
Go
you hear
ahead.
me? So we said for our problem that the delta G was positive, correct?
Yes.
And what you just drew on the diagram, you said if delta G is positive, then P must be greater than R, correct?
That's correct.
Then how come when we were doing KEQ, making it less than 1, we said that our P was smaller than the
Yeah,
R?
not in energy and concentration.
Okay.
So let's say I have a reactant or a set of reactants that only makes 1 mole of product, but I got 10 moles of reactants left. You following that? So
Yes.
the product number would be 1, the concentration would be 1 mole, and then what's left over would be 10 moles. So that would give you a fraction. Is that right?
Yes.
Which would be less than 1.
Okay.
Yeah. So don't mix up energy and concentration. On the
Yep.
energy diagram on the right, that's energy. In the KQ equation, that's concentration.
Okay, thank you.
Yeah, great question, great question. All right, but any other questions? All right, let's do another one. Same thing, we'll walk it down. All these thermodynamic terms, we'll walk down. And let me say this, so for the activation energy, right, this is what controls the rate. Right, if the activation energy is high, it's a slow reaction. If it's low, it's a fast reaction. All right, let's do another one. Let me cut another one out. I'm gonna do the exact same thing. I'm gonna take off. All right, so let's go through and identify all the stuff, nucleophile, electrophile, put the arrows in, and then we'll talk about the thermodynamic component, the delta H and delta G and all that stuff. So where's my nucleophile in this case? Which one? Oh, it's with the cyanide, right here?
That's right there. The minus.
Yes. Right, that's good. Sometimes it's tempting to say, well, because we define the nucleophile as something that loves nuclei, so it has electrons to give away. Bromine has electrons too, right? But that carbon is actually negative. So a negative nucleophile is always going to be more reactive than something that's neutral. So that's my nucleophile. And then this is my electrophile. Right? And then in the electrophile, because of this dot hole, it's the carbon that reacts. Right? Y'all following? Carbon that's reacting, not the bromine. So when the nucleophile attacks, it's going to find that positive site in the electrophile. So it's coming here. Right? What is bromine in this case? What would we call it? Leaving group. Good. Leaving group. What type of reaction is that? Substitution. It's a substitution. Like we lost a leaving group, it got replaced by an incoming nucleophile, so it's a substitution. All right, now let's calculate delta H. Right, we broke a CBr bond, didn't we? Broke that, and then we made a CC sigma bond. Is that right? This is the bond that we made right here. This is the bond that we broke. Broke the carbon bromine bond, we made a carbon-carbon sigma bond. All right, let's go back to the chart. So for carbon, carbon, carbon bond is 347. 347 kilojoules per mole. Carbon bromine bond, which is bromine right here, is 285. That's how much it costs to break a carbon bromine or to make it. As if you make a carbon bromine bond, that's how much energy you get. If you break it, that's how much energy it takes to break it. So 347 and 285. So this is going to be 285 minus 347. And this is in kilojoules per mole. That's my unit. I just didn't write it out, but y'all want to keep that. Keep those units. What is that? 62? Negative 62. Good.
Yeah, I think negative.
Yeah, you're right, it's negative. But again, that's why the numbers actually matter and the sign matters, because if we just said it was 62 and we assumed it to be positive, then we'd be wrong because we'd be saying that's an endothermic reaction and it's not. All right. So negative 62 kilojoules per mole, which means what? Endo or exo? If delta H is negative, that means it's what? Exothermic. All right. Everybody okay so far? Reagan, I see you nodding. That's good. Does that mean it's clicking? I don't know how many of you watched because I sent a bunch of videos. I don't know how many of you watched it, but it will crystallize everything. I see you, Cameron, you said you did watch it. Is it connected? Good. All right. So what do we know now? If delta H is negative, what is the Gibbs free energy? Delta G negative. Delta G is also negative. What about the activation energy? Both. Right? That means the reaction is spontaneous. If it's giving off energy, you don't have to add energy. It just happens, right? So it makes it spontaneous. So delta G, and what about the K and Q? What is it? Less than 1 or greater than 1? It should be greater than 1, right? Because remember, this is P over R. So in this case, that little R left, and has about a P formed. If that's your equation for K and Q, product concentration of the products over concentration of the reactants, then K and Q should be greater than 1. Small number on the bottom, bigger number on the top. Divide them, you should get a number that's greater than 1. All right. Now, what does the energy diagram look like for this? We have a exothermic reaction where this is the reactants, this is the products, right? And this is the transition state. Every reaction goes through a transition state. All right. And this is gonna allow us to talk about one other concept. That I have a video for it, but I didn't send it because we can actually talk about it. All right. So what is this is the activation energy. This is how we know it's low, right? That's my activation. So if that controls the rate of an exothermic reaction is much higher or much faster than the rate of an endothermic reaction. Much faster rate than endothermic. And the delta G we can calculate here. right, which is going to be the energy of the product minus the energy of the reactant. Notice the product way down here, small number. Energy is increasing in this direction. Right, the energy of R is much greater than P. Let's look where it is in relation to P. If we say the energy is increasing from bottom to top. Right? So yeah, P is going to be a small number, R is going to be a big number, delta G is going to be negative. All right. Questions? Any questions about anything? All right. Let's do another one. But I'm not going to do we won't do the energy diagram. We'll go calculate everything else. All right, let's do this. In this case, there is no nucleophile or electrophile. But there is a type of reaction that happens. What is it? You're doing the third. It's an elimination. Right? There's no nucleophile or electrophile. This is intramolecular. So what happened though? What did I do?
One of the electron and oxygen supply.
Okay. What did I lose?
Okay, so you draw another on here.
Is that right? Is that right? All right. I agree with that. And that's really, if you take the first reaction you did and that one and put them together, overall, it's a type of addition followed by elimination. All right. What do we break? No single one. Good. What do we make? We made a CO5, is that right? Is that right? We broke a CO sigma bond and we made a CO pi bond. So let's calculate delta H. We know the CO pi bond is 741, 742? 741. I think the CO sigma is something like 300. So that's fine. Have a chart. Right, so carbon, oxygen. $360. Carbon, oxygen, single bond is 360 kilojoules per mole. 360 minus 741. Delta H, what is that? 381. Negative 381. Is that right? About energy. Anybody not following online? Anybody have a question? Is my math correct? 360, 741 minus 360?
Ready.
I think so. What do you think, Ken? You're like, where? Just hurry. We got 9 minutes left. All right. So what does all this mean? Delta H is negative 381. Highly exothermic. Highly exothermic. You're right. So it's exothermic. What do we know about, what can we say about KQ? Is it greater or less than 1? Greater than 1. What can we say about delta G? Not the activation in the field. It's positive, right? Or negative. And what can we say about the activation energy? Oh, oh. Fast reaction. If we took the two, the top step and that step, the top reaction, which we did already, which is right here, if we took that and this and combined them, because this is really one reaction. It's an addition followed by an elimination. If we combine them, we could get the overall delta H. What do we calculate for that person? 300, 400 or something? The first, this reaction rate up top. 430 positive. So positive 436 and then negative 381. What is that? 55. Is that 55? Something like that? Yeah, I think it's positive 55. So overall, if we combine those two together and summed up the energies of each step, this overall is going to be endothermic, but only slightly. So a reaction like this, you'll probably have to add in some acid or something to catalyze it because it's slightly endothermic. But we'll talk more about that later. Any questions about anything? All right, I'm gonna give y'all, what time is it? 3 minutes to do the next one. If you're here in the room, you can work together without being all up on each other. Y'all know, it's still real out here. All right. So 3 minutes. Normally, if the class was fully in person, like that's what we would do. We'd be sitting in groups working through these, not me just writing all the answers out. But we can't do that right now. So go through all the steps, what type of reaction, find the nucleophile, find the electrophile, put the arrows in, and then do the thermodynamic part 2. How confident do you feel about this right now? On a scale of 1 to 10? 7, 5, 4? Is that a 4, a 5? Okay. The other 5 will come with practice. The more you do it, the more confident you're gonna get. What about y'all? I ain't leaving out the Zoomers. How confident do you feel about this right now on a scale of 1 to 10? Don't put it in the chat because I can't see it. You got to unmute.
A 5.
5? Okay. You got, I'll give you an extra. You need me to zoom in on? No, Does anybody have the nucleophile identified? Which one is it? Oh, this is the nucleophile. Good. By default, that's the electrophile. Anybody put the arrows in here? What did you do? Right here? Great, excellent. That's exactly right. So now, let's do the thermodynamics. What's the delta H? What bond did we break? Carbon chlorine, and we made a carbon nitrogen. Don't we already have that number for carbon nitrogen? What is it? Well, the bonds formed is 305. And then the bonds broken, let's grab that right quick. It is carbon chlorine. 339. Based on the chart. Carbon is here, chlorine is here, so it's 339. All right, let's put that in. What is that? Plus positive 34. Kilojoules per mole. But we know once we calculate that, we can estimate everything else. Is that right? So what is the activation energy? Is it hot? First of all, is it exo or endothermic? Endothermic. Not highly, but it's endothermic. All right. So we know that the delta, the activation energy is going to be high. You know, delta G, gift free energy is going to be positive. Is that right? And KQ is going to be what? Less than 1. All that stuff we can extrapolate again from knowing delta H. We can calculate delta H for any reaction if we know the bond energy. All right, we're gonna stop right there. I'm gonna give y'all a minute back today. Out of 50. Really gave more because we started late. Any questions online?
Yes, what type of reaction is this?
Oh, good question. What type of reaction is it? It's a substitution.
Okay, thank you.
And it's a substitution because, it's a substitution because the nitrogen replaced the chlorine.